The next chapter, area of a part of a circle. In this chapter, we will study the area of sectors and segments of circles. O is the center of a circle. A and B are 2 points on the circumference. APB is an arc of the circle. OA and OB are 2 radii of the circle. The portion of the circle is bounded by 2 radii and an arc. This portion is called a sector of the circle. In this figure, the sector is bounded by 2 radii, OA and OB, and the arc APB. This sector is named as AOPB. The angle subtended by an arc at the center of the circle is called the central angle. It is denoted as theta. If theta is less than 180 degrees, the sector is called a minor sector. If theta is greater than 180 degrees, the sector is a major sector. If theta is 180 degrees, the sector is called a semicircle. If theta is equal to 90 degrees, the sector is 1/4 of the circle and it's called a quadrant. We can calculate the area of a sector of a circle if we know the radius of the circle and the central angle. The area of the sector is proportional to the area of the circle. The central angle is proportional to the angle in a circle. Therefore, area of a sector over the area of a circle is equal to theta over 360 degrees. If we do cross multiplication, area of a sector times 360 degrees is equal to theta times the area of a circle. If we divide both sides by 360 degrees, area of a sector is equal to theta over 360 degrees times the area of a circle. Area of a circle is given by pi r squared, and so area of a sector is equal to theta over 360 times pi r squared. For example, given a circle of radius 6 centimeters and a central angle of 140 degrees, we can find the area of the sector OAPB. Area is equal to theta over 360 times pi r squared. That is equal to 140 over 360 times 22 over 7 times 6 times 6. And so we remain with 22 times 2, which is equal to 44 centimeters squared. In another example, a sector of a circle subtends an angle of 120 degrees at the center and has an area of 462 square centimeters. Calculate the length of the arc. In the solution, we know that arc length is equal to theta over 360 times 2 pi r. So to be able to calculate this, we need to find the radius first. Recall the area of a sector is equal to theta over 360 times pi r squared. And so 120 over 360 times 22 over 7 times r squared is equal to 462 square centimeters. By 121 by 120 is 3. And so we shall have 22 times r squared over 3 times 7. That gives us 22 over 21 r squared is equal to 462. To remain with r squared on one side, we multiply both sides by 21 over 22. So by 22 by 22, 21 goes with 21. 462 divides into 22 21 times. So we remain with r squared is equal to 21 times 21. We do not have to complete 21 times 21. We remain with r squared is equal to 21 squared. And so r is equal to 21 centimeters. Arc length is equal to 120 over 360 times 2 times 22 over 7 times 21. And that gives us by 121 by 123 by 31 by 37 by 71 by 71. That gives us 44 centimeters. Next, we look at the area of a segment. O is the center of the circle. AB is a chord on the circle. APB is an arc of the circle. The portion of the circle bounded by the arc and the chord is called a segment of the circle. In this figure, the segment is bounded by the chord AB and the arc APB. This segment is named as APB. Observe again the sector of a circle. It consists of two parts. One part is a triangle and the other is a segment. The area of the sector is equal to the area of the triangle plus the area of the segment. And so the area of the segment is found by subtracting the area of the triangle from the area of the sector. For example, given the central angle as 120 degrees and a radius of 7 centimeters, we can find the area of the segment. First, we find the area of the sector. That is equal to theta over 360 pi r squared. This is equal to 120 over 360 times 22 over 7 times 7 times 7 by 121 by 123 by 71 by 71. 22 times 7 over 3 is equal to 51.33. So our area is equal to 51.33 square centimeters. Now we need the area of the triangle AOB. We can drop a perpendicular from O to AB. This will give us two equal right-angled triangles with hypotenuse 7 centimeters and an angle of 60 degrees each. Name this point C. We can now find the length AC, and this will be equal to the length CB. We can say that sine 60 is equal to AC over 7, that is opposite over hypotenuse. Cross multiplication, AC is equal to 7 times sine 60. From the tables, sine 60 is equal to 0.8660. So AC is equal to 7 times 0.866. That gives us 6.06 centimeters. The length AB is twice this length. So AB is equal to 2 times 6.06, and that gives us 12.12 centimeters. Now we have all the three sides of a triangle. We can apply the Heron's formula. Area is equal to the square root of S times S minus A times S minus B times S minus C. S is half the perimeter of the triangle. In our case, S is equal to a half times 7 plus 7 plus 12.12. That gives us 13.06. Area will be equal to 13.06 times 13.06 minus 7 times 13.06 minus 7 times 13.06 minus 12.12. That is equal to 13.06 times 6.06 times 6.06 times 0.94, everything square root. That will give us the square root of 450.83. The square root of that is 21.23, and so the area of the triangle is 21.23 square centimeters. Area of the segment is given by the area of the sector minus the area of the triangle. That is 51.33 minus 21.23. That gives us 30.1 square centimeters. Lastly, area of intersecting segments. In this diagram, we have two circles with centers A and B with radius 3 and 4 centimeters respectively. The distance between their centers is 5 centimeters. Their segments intersect, creating a common region colored green. We want to calculate the area of the green portion. Basically, what we do is simply find the area of each segment and then add them up. Your knowledge on triangles and angles will help a lot. And there's lots of ways you can approach this. Now let me bring this 5 centimeters up here to have AB. Now we have a triangle ABC. Now this is interesting. If you recall the Pythagoras theorem, for a triangle with these measurements, then this angle is 90 degrees. And this is just pure coincidence. So we are actually dealing with a right-angled triangle here. Let me name this angle here theta and this one beta. Using trigonometry, we can find theta and beta. It's important you see that AB is the hypotenuse here. And so sine theta is equal to 4 over 5. This is equal to 0.8. Sine theta is equal to 0.8. Finding the inverse on both sides, theta is equal to 53 degrees. For beta, sine beta is equal to 3 over 5. 3 over 5 is the same as 0.6. The sine inverse of 0.6 is 36.8 degrees. Now with these angles, let's now complete the other two radii and mark this one D and draw line CD. We can now find the areas of the sectors. Before we proceed, common sense will tell you that the central angles will now be twice those ones we have calculated. Now, area of the sector formed by the small circle, we give it AS. So AS is equal to 106 over 360 times 3.142 times 3 times 3. By 3 1 by 3 120 by 3 1 by 340. So 106 times 3.142 divided by 40 gives us 8.33 square centimeters. Area of the bigger sector, 76.3 over 360 times 3.142 times 4 times 4. By 4 1 by 490. So 73.6 times 3.142 times 4 divided by 90 gives us 10.28 square centimeters. Next is the area of the triangles. Now, one big mistake you are likely to make is to assume line CD bisects line AB, and therefore assume we have 2.5 centimeters. That is not true. The circles have different sizes, and the figure ACBD is actually a kite. One thing is true though. The line CD bisects the angle at C and D. Also, line AB will bisect line CD. So this angle here is 45 degrees and these two lines are equal. We can now find CO. Cos 45 degrees is equal to CO over 4. That is adjacent over hypotenuse. CO is therefore equal to 4 times cos 45. Cos 45 is equal to 0.7071. 4 times 0.7071 gives us 2.83 centimeters. And so if CO is 2.83 centimeters, then CD is twice this length. That is 2 times 2.83. That gives us 5.66. Now we have the triangles with all the three sides. We apply the Heron's formula. The smaller triangle first. S is equal to 3 plus 3 plus 5.66, everything divided by 2, and that will give us 5.83. Area of the small triangle will be square root of 5.83 times 5.83 minus 3 times 5.83 minus 3 times 5.83 minus 5.66. That will give us 5.83 times 2.83 times 2.83 times 0.17. That gives us 7.94, square root of which is 2.82. So the area of the small triangle is 2.82 centimeters squared. Now subtract this from the area of the small sector to get the small segment. That is 8.33 minus 2.82, and that gives us 5.51 square centimeters. We go to the larger triangle. S will be 4 plus 4 plus 5.66 divided by 2, and that will give us 6.83. Area is equal to 6.83 times 6.83 minus 4 times 6.83 minus 4 times 6.83 minus 5.66, square root of everything. That gives us 6.83 times 2.83 times 2.83 times 1.17. That should give us the square root of 64, and that is equal to 8 square centimeters. Now subtract this from the area of the big sector to get the area of the segment. 10.28 minus 8, that gives us 2.28 square centimeters. Now add up the area of the two segments. 5.51 plus 2.28 gives us 7.79 square centimeters.
The second thing I love about math is it's a puzzle-solving kind of, if I can figure it out, and the joy of figuring it out, the kind of sense of accomplishment, the sense of excitement when you get it, the challenge of trying to get it. It's that puzzle-solving kind of thing that I really, really like.